Hey folks, another video today about super caching on Zuplo. First of all, let's take a quick look at how caching actually works on Zuplo using the caching policy that we have. So here's a little diagram. We have a client here. It makes a request that typically hits the caching policy. The caching policy then looks, do I have a stored entry for this request that matches this request? And there's lots of configuration options on the caching policy that allows you to identify which properties, which attributes of a request you want to cache on. If there is an entry, then it will immediately send a response. Now, one great thing about Zuplo is we're an edge-based gateway. So that means we deploy you to one region, Earth, everywhere, all at once, all of the time. And so you're within 50 milliseconds of almost every human on Earth. So this cache response is crazy fast. If there isn't a response ready in the cache, then we'll just run through the normal pipeline. So we'll run your other request policies, we'll run the request handler, that will hit your backend API, and then the response will be sent. And of course, the caching policy will then capture that response so that it can be used for a future request that meets the same caching criteria. I was recently approached by a customer that loved this, wanted this feature, but actually had a pretty sophisticated set of caching requirements. So they wanted to have different caches per customer, and then customers would actually have different applications. So here we have a customer A who has two applications, A1 and A2, and then you might have a customer, sorry, this should be B, that would have application B1 and B2. Now the caches for these should be distinct and separate and not shared for those applications. It's an important thing. Now, that's quite possible with Zuplo. If you look at our caching policy, I'll just show you this now. You'll notice it has an option called cache ID. So this is an option that can be specified that kind of creates a clean namespace for the caching policy. So if we make that cache ID some unique name that maps to application A1 and application A2, then the caching data will never be shared across that cache ID. And in this demo, what I'm going to do is actually show you how we can do this programmatically. Now, the other thing this customer wanted to do was to be able to programmatically or procedurally bust this cache. So bust the cache for A1 or bust the cache for A2 and make that happen fairly quickly. So I'm going to show you the proof of concept I put together and just how you would do this. And I'll show the source code in a GitHub repo towards the end of the video. Okay, so let's go and take a look at the solution. So what we did here actually is we're going to use a JOT authentication policy. We're going to generate a JOT token, and the JOT token in this case, what it's going to do is it's going to have a property customer ID inside the payload that we look at. The application identifier is going to come in on the request header. And so this JOT auth policy is just a standard JOT authentication policy. This custom cache, and actually I have a token here that I can share with you. So let me show you this in jwt.io. If we take a look, you'll see this has a customer ID, customer A, built into the policy. And then we're sending an application A2 header here. So when I send this request, it's going to hit that cache response, and there's going to be a distinct cache for application A2, application A1, etc. And I'll show you how we're doing that. So one of the things we're doing here is we're using a custom policy called custom cache. And if we take a look at this policy, it's pretty straightforward. All it does is actually wraps our built-in caching policy, but dynamically sets the options. So let's take a look at this code. Let's walk through it. Here, I extract the customer ID from the payload in the JOT token, okay? I take a look for the application ID in the header. If I didn't have a customer ID, I'm going to throw an error saying there was no customer ID found in the user metadata. That will log an error and will return an internal server error to the customer. You might choose to return a bad request for this. In this case, if there's no application ID in the... let me explain that actually. The reason I decided to throw an error here is you're responsible for issuing JOT tokens and signing them somewhere through your IDP. So it's up to you to make sure it has the right payload in. Hence, I decided to go with an internal error here. But the request in this case, I designed it to send a header. So it'd be easy for a user to forget to send the header, in which case we want to send a bad request saying no application ID header was provided. You need to verify that you trust that that user has access to this application ID. I'll leave that to you, pretty easy to do. So now what I do, now I've confirmed that I have an application ID and a customer ID, I'm going to use this thing called the cache key loader. I'll show you that in a second. That's actually going to load a bunch of metadata from an external data source that stores our unique cache keys that are going to be used as the cache ID for each of these applications. And this is important because one of the ways we can bust the cache is to change that unique cache ID. That will essentially create a new cache and let the old one just retire out. So I'm going to load all cache keys for all applications in my solution here. And I'm gonna do that using the background loader component that Zuplo provides. I'll talk you through that in a second. And then we're going to scan all of those cache keys to find a cache key that matches my application ID and my customer ID. If I didn't find one, I'm going to throw a new internal server error again. My assumption here is you have your database set up correctly or your data source set up correctly. And then based on this, if we look at what this loads up, it loads up a type called cache key. And that is here, that has a customer ID, an application ID, a time to live seconds, so we can set the TTL per application ID, and that unique string that is the cache key to be used as the cache ID. It loads that up, and it then generates the caching inbound policy options. It then invokes that policy. You can actually call our policies programmatically like this, passes in the options, just reuses the policy name of this policy that I've created here. And also I check to see if there was a cache hit or miss because I wanted to log that. So I just simply look at whether the result of the calling this policy was a response or a request. If it was a response, then I know I had a cache hit. If it was not, it was a cache miss. So I'm going to log that, say cache hit, and I log the cache key as a little bit of extra information. And then I return that result. So we just created a very thin wrapper around the caching inbound policy that helps me basically build an enhanced caching policy that has this super cache busting. So where is this cache key data coming from? Let's look at this. Actually, I decided to use Supabase. So I have a database table in Supabase that looks like, let's take a look at this. Coming over here to my database, cache keys, I'm gonna just edit the table that looks like this. So it has a customer ID and an application ID. Those are the primary keys, so they, in combination, have to be unique, which is good. It then has a cache key property, which I think we also require is unique, so it cannot be the same in any table. And it has a TTL seconds value, which is an integer, and then just a created at column, which is pretty common. This table, if we take a look at the data, if I view the table, has an entry right now for customer A and application A2 and customer A, application A1. And notice it has some cache keys. It really doesn't matter what's in here as long as it's a unique string, and I'll show you how that works. So the way I've set this up is I am invoking a little service here that's a service we use for things that is essentially a counter API. So let me show you how this works actually. It's kind of a fun little API we have. So I'm going to put some unique string here, and every time I hit this, the counter will increment. This is useful for testing caching, because if I don't hit it, the counter won't increment. If I'm returning a cached response, the counter won't increment. So I'm going to copy this and use this as my backend. I'm going to say bananas extra random. So it's just some random string that will give me a fresh cache count. I'm going to save that change, wait for that to deploy here. Should just take a couple of seconds, okay? And then when I test this, my expectation is the first time I won't have a cache entry. Oops, what did I do wrong? Oh, yeah, sorry. I need to update the URL here. Cache demo, that's it. Hit test. And I don't have a cache entry, so I get a 1. It does actually increment. Then the next time I get a 1 again, and that's because I'm using my super cache. So this is, remember, a cache per application. Now, what I also want to do though is actually show you how I can bust this cache. So I'm going to programmatically bust this cache. It's going to be very easy. What I'm going to do is come in here, and if you remember, I'm actually doing application A2. So if I look at application A2, I'm just going to change this to be some other unique string. There you go, I'm pretty sure that should be unique. And if I come back and hit test, I get a 2, showing we just bust the cache. But that's going to be the same. I'm I'm going to keep getting a 2. I set the cache settings on this for a long time. If you look here, I set them to be 60 seconds, so 1 minute of cache. You can vary that. I'm going to change it again. Come back here. And it might just take a second for the background. Oh, did I not save that change? Oh, I changed the wrong one. Yeah, I busted the wrong cache, sorry. So if I change this to be 2, that's right. Come back, and now I get a 3. So I just showed you that cache busting. Now, how does this work? How do we load in that cache? Well, we're using a function called the background loader. The background loader will keep reloading configuration data, but it'll do it quite efficiently. It'll make sure there's only one request at a time. So I have a function here called load cache keys that simply loads up that table from Supabase and returns it. But the nice thing is, we're not doing this for every request. We're doing it once continually, essentially just like keep reloading it. So that means that data is going to be pretty fresh. We could actually make this more delayed if we wanted to, but for now, I think it's fine to just do it. As much as there's sort of active traffic on the gateway, it'll keep trying to load it, but no more than one request to that configuration service at a time. So there you go, that's super caching on Zuplo with a dynamically bustable cache per application or any kind of sort of scoping combination that you like. I'm gonna push this to GitHub. Let's do that right now. As a public, I'm gonna call it super cache actually. I'll put it in my personal cache. I will connect this project and I will share this super cache. There you go, github.com/JoshTwist. That's super cache. The code for this demonstration I've just shown you is all in here. So yeah, go have fun.